All right. So far in chapter 6, and we started out talking about our chemical equations and balancing our chemical equations. Okay. Then we worked into talking about the mole and our molar mass, okay, using our grams our grams per mole to be able to convert between the two. Now what we want to do is kind of combine this concept of molar mass with our concept of this balanced chemical equation, why it means something for us. And basically what we're looking to do is we're going to determine some mole relationships in our chemical equations. So section 6.6. So your book calls these mole relationships, and they call them, they say mole relationships. They call these, or they refer to them as mole-to-mole factors, or mole-to-mole ratios. Same kind of concept there. To the rest of the chemical world, we call this, it gets a special name called stoichiometry. So that's Stoichiometry. So stoichiometry. So it's basically the study of these mole relationships. Okay? And what we're going to do, okay, how we use this concept of stoichiometry is we're going to use the coefficients of our balanced chemical equation, okay, to relate or convert between moles of one substance to moles of another. So if we look at kind of a simple chemical equation, and we'll look at the combination of aluminum and chlorine. So if we have aluminum as a solid, and we're going to combine that with chlorine, which is one of our diatomics, so it comes as a molecule, and it's found in the gas phase. If we combine these together, we're going to get aluminum chloride, following by our rules of chapter 5. Aluminum is a metal, chlorine is a nonmetal, so this is an ionic compound. Aluminum forms a 3+ charge, chlorine a -1, so we have AlCl3, and our ionic compounds are found usually naturally in a solid state. Now remember, we need to use a balanced chemical equation, so this is not balanced so far. Okay. So my chlorines come in packs of 2 as I'm starting. They're going to be ending in packs of 3. Okay. So hopefully you've gotten used to balancing, but basically when I see something like this, Okay, I know I'm going to have to basically double up on one of my coefficients. Okay, so I have 6 chlorines that I end up with, so I need to start with 6 chlorines. Okay, so I put a 3 out in front. I ended with 2 aluminum, so I need 2 out in front. So if we look at kind of this concept of stoichiometry in words. If I were to describe this relationship here in words, and basically what it means is for every 2 moles of aluminum that react with 3 moles of chlorine, 2 moles of aluminum chloride are formed. So this 2, okay, from my 2 moles of aluminum, that's coming from this 2 here. And I'm reacting that with 3 chlorines. Might not be able to see the difference of this, so maybe I'll circle this one. Our 3 chlorines come from that 3 in front of chlorine, okay, the Cl2. Okay, notice that I haven't involved this at all. Okay, so even though this does have chlorine and it does have aluminum, okay, that hasn't come into play until we talk about these 2 moles of aluminum chloride that are formed. Okay, so maybe I'll kind of ran out of basic shapes. I'll do this in a kind of, I don't know. So those are where those relationships come in. Now, we want to get this into a way that we can use this for calculation. Okay, so where this stoichiometry really is, okay, or in the case of your book, they call these the mole to mole factors. Okay, or ratios. Your book could use that word, I don't remember. Okay. Basically, we can look at 2 of these at a time. Okay, we can't look at all 3 because we're going to be doing calculations with them. So we can only compare 2 at a time. But what we're going to do is we take these coefficients to develop these mole-to-mole factors. Okay, so for every 2 moles of aluminum, that's going to be the equivalent, or we have the ratio of 3 moles of chlorine. Or we can also look at 2 moles of aluminum to 2 moles of the aluminum chloride. Or our last relationship, our last ratio, we have 3 moles of chlorine to 2 moles of aluminum chloride. So basically what we do is we have equivalents here. Okay? Remember our equivalents we can write as conversion factors. So if I take this, these are our conversion factors. or we can write them more looking like a ratio here. We have either 2 moles of aluminum for every 3 moles of chlorine. Or we have the flip-flop of that. You have 3 moles of chlorine per 2 moles of aluminum. And we can write conversion factors also for these other 2 examples. Same thing, same concept. All right, so let's work through an example. I'm going to go ahead and start a new page. I don't have quite enough room there to really show this example all on one page. So we're going to use the formation of ammonia. Okay, so we have nitrogen plus hydrogen. This is ammonia, NH3. Okay. We want to answer 2 questions. Okay, first of all, I want to ask, what are the multimole factors? Okay, so multimole factors are these here. So we have 3 different compounds here. So we're going to have 3 different multimole factors. Okay, so we have 1 mole of nitrogen, okay, from the coefficient out in front. And that's the mole-to-mole factor with hydrogen is 3 moles of hydrogen, taken from that coefficient. Or we can look at 1 mole of nitrogen to 2 moles of ammonia, the NH3. Or our third relationship, we have 3 moles of hydrogen to 2 moles of ammonia. So those are our mole-to-mole factors. Okay, that will allow us to kind of help us look at doing some calculations. So let's look at how many moles of hydrogen are needed to react with 1 mole of nitrogen. So how many moles of hydrogen are needed to react with 1 mole of nitrogen? Well, hopefully most of you are saying that we have 3 moles of hydrogen. Because if we look at our mole-to-mole factors, if we have 1 mole of nitrogen, we need 3 moles of hydrogen. Now, sometimes that gets a little bit more complicated. It's not quite as straightforward. As what about 0.6 moles of nitrogen? Well, some of you who are whizzes at math can do that really quickly. It's a 1-to-3 ratio, so multiply that by 3, you get 1.8. Okay, awesome for you. For those of you who have no idea what and how I got to those numbers, I'm going to show you the math of how we get there. Okay, basically what we're using, what we want to do, is we're going to use our coefficients, which is how we got to these, as conversion factors. So we're going to start with our 0.60 moles of nitrogen. We want to convert from moles of nitrogen to moles of hydrogen. So we put moles of nitrogen down in the denominator so that these units cancel. And we want to convert to moles of hydrogen. Now notice I'm using 2 units. These are both moles, so it's very important to label your moles as to what compound you are looking at. Okay, don't leave these just as moles because then you're going to get confused. So we're always going to have moles of something, moles of something. Okay, same when you put grams. You want grams of something, atoms of something. Okay, always have those 2 components there. Okay. So to fill in this ratio, we can use these multiple factors that we wrote out. Or what you'll find as you get used to this is you can just use your coefficients from your balanced chemical equation. Okay? So our coefficient for nitrogen is 1. Okay? Our coefficient for hydrogen is 3. So we can draw, I'm going to make a little mess of the notes, but show you where these numbers come from. Okay, our 3 comes from our coefficient in front of hydrogen. Our 1 comes from the coefficient out in front of nitrogen. Okay, 1s are usually left off. So to do the calculation, you take your 0.60 times 3, and you get 1.8 moles of hydrogen. All right, let's work another example. Okay, still using this same balanced chemical equation here. Okay. I want to know how many moles of ammonia are produced when 1.4 moles of hydrogen react. Feel free to take a stab at this. Okay, I'll leave the equation up there. So pause the video, take a stab at it, and I'll have your explanation when you return. All right, so we've been given 1.4 moles of hydrogen. We want to know, or we need, moles of ammonia. Now, anytime in any type of calculation, basically from the rest of this point, or excuse me, from this point in the quarter on, okay, anytime that you're starting with one component and moving to another, you have to use stoichiometry. Okay, you have to use these mole-to-mole factors. That is the only way to convert from one compound to another. Okay, I'll say that again. If you are starting with one compound and moving to a different compound in your calculation, the absolute only way to do that conversion is to use stoichiometry, is to use those multimole factors, okay, using those coefficients. That's the only way to do that conversion. So we want to start with our 1.4 moles of hydrogen. Set up our conversion. Moles of hydrogen is up top, so we want to put that down in the bottom. Remember, we want those two components always have moles of something, atoms of something, grams of something. So moles of hydrogen was up top. We put moles of hydrogen down in the bottom. We're trying to calculate to moles of ammonia. So we're going to put moles of NH3 up top. We want to get these numbers from our coefficients of our balanced chemical equation. So our coefficient in front of NH3 is a 2. So we put a 2 in front of our moles of NH3. Our coefficient for hydrogen is 3. So we'll put that down there. And now we can calculate this out. 1.4 times 2 divided by 3, and we get 0.9333333. We only need 2 significant figures, so 0.93 moles of ammonia is our final answer. So again, make a little bit of a mess of the notes, but just to show you again where those numbers came from, I'm going to keep it color-coded. The 3 from the hydrogen, okay, was that same 3 that we used up in the previous example. Okay, that's coming from that coefficient in front of hydrogen. Use my pink color here for the 2. This 2 comes from the coefficient in front of ammonia. Basically we have 2 is pink, the 3 from hydrogen is green, and the 1 that's left off from nitrogen is our red.